Hello everyone, thanks for joining us. In this demo, we'll be walking you through our PCB XL ECG project directly from our notebook. We'll show you how we prepare the dataset, train a baseline 1D CNN, and then audit intersectional fairness across age and sex on the unseen test set. At the beginning of this notebook, we import the core libraries we needed. NumPy helps with numerical work. PyTorch is what we use to build and train the model. Pandas organize the metadata. Skyscape learn helps with pre-processing and evaluation. WFDB reads the ECG signal files, and TQDM gives us progress bars while longer tasks are running. We also global C42 reproducing the same training setup can be repeated consistently. That matters a lot in research because it lets us know that any changes we see later are due to the model or the method, not random chance. Then we download the PTB XL dataset from SitesNet, extract it into Colab, and we verify that the files were saved correctly in the context as you see at the bottom of the screen.
Next, we move into the data preparation stage. We load PTP-Excel dataset.csv and SCP statements.csv, then map the detailed SCP codes into the 5 superclass labels we care about. Those labels are normal, myocardial infarction, STTC, conduction disturbance, and hypertrophy. We convert them into the binary multi-label format using multi-label binary erasure, which gives us one target vector per ECG. After that, we follow the official strat-fold splits with folds 1 through 8 for training, folds 9 for validation, and folds 10 for testing. This is important because it gives us a proper benchmark setup with no patient leakage, so the test results reflect performance on completely unseen patients. In other words, we are evaluating the model on patients it has never had access to during training.
Then we define a custom PTB-XL dataset class. This class is what actually loads each ECG waveform, standardizes the 12 leads, and returns the waveform, the label vector, and metadata like age and sex. That metadata is especially important because later on we will use it for our fairness analysis. And after that, we build data loaders with batch size 32, and a quick sanity check confirms the expected input shape of torch.size 3212,1000 and label shape of torch.size 32.5. So at this point, we know the data is flowing into the model exactly the way we expect, and we can trust that the input pipeline before moving into training.
Next is the baseline 1DCNN ECG 1DCNN module. This module uses three 1D convolutionary block, max pooling, and adaptive average pooling to trust each ECG into the compact feature representation. The first layer learns low-level waveform pattern, and the deeper layer learns more abstract signal features that are like useful for diagnosis. Then a fully connected classification converts those learned features into 5 logics, one for each diagnosis superclass. We also run a sanitary check with we also run a sanitary check with dummy ECG data to confirm the model produces like prediction with shapes 32 and 5. That tells us that the architecture is wired correctly before the training begins, and the output dimension matches the 5 labels tags we are solving.
Then we train for 10 epochs using AtomW and BCE with logits loss. AtomW handles the weight updates, and BCE with logits loss is the right choice here because this is a multi-label problem where more than one diagnosis can be present in a single ECG. During training, the model repeatedly sees batches of ECGs, makes predictions, compares them to the ground truth labels, and updates its weights to reduce error. The training loss drops from about 0.4081 to 0.3013, while validation loss improves to a best point around epoch 9 before rising slightly at epoch 10. That pattern suggests that the model learned useful structure in the ECG signals, but also started to show mild overfitting near the end. So overall, the model is learning well, but the validation curve tells us exactly where performance begins to plateau. We then save the model checkpoint so we can reuse the exact trained model later without retraining, which is useful for both analysis and future experiments.
Finally, we ran the finance audit on the unseen test set. The audit group patients by the age and sex, young male, older male, young female, and older female, and computes the false negative rate for each diagnostic classes. A false negative means the model missed a condition that is actually present. So this is especially important in healthcare, where missing disease can have like serious consequences. The feature shows that the model does not fail evenly across the groups. For MI condition, female have like a noticeably high missed rates than other groups. For the CD condition, young women are also hit hardest, and for the HYP condition, the model misses most class across all groups, which tells us that the class is especially difficult for the baseline model. That is exactly why we're running the intersectional audit rather than just like reporting a single global matrix. And it basically gives us like a clearer picture of where the model is strong, where it is weak, and which patients group may be at the greater risk of being missed. Thank you.